This is joint work with Willy Zwaenepoel from University of Sydney. And today I'm going to talk to you about two contributions of our paper. The first one is size-aware sharding. It is a technique to improve the tail latencies of in-memory key value stores with heterogeneous height and sizes. And the second contribution is the implementation of size-aware sharding in the new Minos in-memory key value store that we show is able to achieve one order of magnitude improvements in the 99% latency of memory key value stores. So I think I don't have to convince you that tail latencies are very important nowadays, especially for high fan-out applications. In these applications, one request of the user translates to multiple sub-requests to different servers, and the slowest reply to these sub-requests determines the overall latency perceived by the user. So the SLO nowadays is not about mean value of the response time of the servers, but typically takes the form of the nth percentile of the response time of the latency of the server has to be within a given threshold, where the n parameter is typically very close to 100, for example, 99. In-memory key value stores are a widespread solution to reduce the latency for data platforms. They are in particular used as caches or non-persistent data repositories, as we have just seen. But of course, they are also used as main backend data platform for large-scale applications. And in-memory, state-of-the-art in-memory key value stores achieve very good performance by a combination of design choices. First of all, they implement kernel bypassing network stacks on top of high-performance NICs with multiple parallel queues. And they also employ very efficient runtime completion models that are coupled with ad hoc data structures and concurrency control schemes. And by the combination of this technique, they achieve very, very good performance. They can scale to millions of operations per second while maintaining latencies that are in the order of the microsecond. However, what we also find is that these designs are prone to suffer from high tail latencies when faced with workloads with heterogeneous height and sizes. Now, this can represent a problem because heterogeneity in height and sizes is common. So we find that, especially in production workloads, this happens. Heterogeneity happens. We find heterogeneity in the workload characterization of Facebook, of Wikipedia, of Flickr, and also in the evaluation in the paper that was just presented for Shield. They show that in the memcache deployment of a large-scale memcache deployment, they have that heterogeneity is very strong. And in particular, heterogeneity of the item sizes comes in the form of heavy tail distributions. That means that it's true that the vast majority of the items are very small, and the vast majority of the requests is toward these items that are very cheap to process. But there is also a small fraction of items that is much, much larger, and processing these items is much, much more costly from a computational point of view. This kind of heterogeneity gives high tail latencies, mostly because of two reasons. The first one is head-on-line blocking, and the second one is what we call the convoy effect. Head-on-line blocking is a very well-known problem. It basically consists of small requests being enqueued behind a large request while being served on a core. Of course, if the small request is enqueued behind the large request, the small request will suffer from a high waiting time because it has to wait for the large request to be processed before. The convoy effect is the term we use to represent the phenomenon in which a burst of large requests may take most of the cores or all the cores at a given point in time. And this leaves few resources available for small operations, and then these small operations will pile up to access the free cores, thus leading again to high waiting times and high tail latencies. So to tackle these issues, we propose size-aware sharding. That is a very simple technique that revolves around two main points. The first one is to assign small and large requests to this joint set of cores, and in this way we avoid head-on-line blocking. And the second point is to reserve some cores for small requests, thereby avoiding the convoy effect. So let's see how size-aware sharding works in practice with an example. Assume we have 5 cores on our servers, and assume that size-aware sharding reserves 3 cores for small operations. We call these the small cores. And assume that it allocates 2 cores for large operations, and we call them the large cores. Now, if a small operation arrives from the client, this can be served by a small core. And if a large operation arrives from the client, this operation can be served by the large core. By doing this division, we prevent the scenario in which a small operation is enqueued behind a large request. So we avoid the head-on-line blocking problem here. Now assume that also another large request arrives and takes the second large core. What size-aware sharding also avoids is the combo effect by preventing that if other large operations arrive, they take the small cores. This is also prohibited. So by doing this, we avoid the two aforementioned problems, headline blocking and the combo effect. But of course, we hit a trade-off because large requests may take longer to complete. We see this in this other example. When we have the all cores are taken, we still have 3 cores for small operation, 2 cores for large operations. If a new large operation arrives, in size-aware sharding, this large operation can be served only by a large core, incurring the response time in red. In other approaches without size-aware sharding, what could happen is that the large request could be served by the other cores that have smaller waiting times, and then they could serve the request with a lower response time altogether. So now let's talk about a little bit how we implement this simple technique in the Minos in-memory key value store. So when implementing size-aware sharding, we have in mind the performance of a single key value store. So even if you have a distributed system with many key value stores, size-aware sharding is intended to be implemented at the level of the single key value store that we assume exposes a simple put-get API. We also assume only the availability of commodity hardware. And as of now, we don't deal with data durability. So size-aware sharding for now primarily targets key value stores that can be used as caches or non-persistent data repositories in general. Now, of course, to implement Minos, we had to make some design choices and to tackle some challenges. And in this talk, I'm going to describe 3 challenges that we had to tackle. The first one is how we determine what is a threshold within a small and a large operation. The second one is how we partition the cores in small and large cores. And the final one is how we implement efficiently the dispatching of the requests to the cores. So to determine the threshold between small and large operations, the main insight we rely on is that if we want to improve the nth percentile of the operations, what we have to do is to improve the latencies of the n% smallest requests. These are the ones that will give you the best improvement in the nth percentile. So let's see what Minos does when n is, for example, 99. So let's see what happens if you want to improve the 99 percentile of the latencies. At runtime, Minos obtains the CDF of the sizes of the accessed items. To do this, the cores profile the workload that they see, and periodically this information is aggregated by one core. Once the CDF is obtained, Minos can determine what is the 99 percentile of the size of the requests that are produced by the client. So then this value acts as a threshold, meaning that any request hitting an item whose size is smaller than the threshold is called a small request, and it goes to a small core. All other requests go to the large cores. To implement core partitioning, what we have to take into account is our 2 antithetic goals. On the one hand, we want to allocate as many cores as possible to the small cores, so as to improve small requests as much as possible. On the other hand, we don't want to remove too many cores from the large requests, because otherwise the set of cores for large requests can become the bottleneck of the system. So what we do, we take a load proportional approach. So if k% of the load is for small requests, then we allocate k% of the available core to small requests. Now, implementing this policy requires us to measure the load that requests have on the system. So we need some sort of function that, given a request of a given size, gives us the load for the request. What we do is we choose a very simple function that measures the load of a request as the number of processed network packets for the request. So if the request is a get, it's the number of packets sent back to the client. If the request is a put, it's the number of packets received from the client. So this roughly measures the amount of memory accesses that are done, the bytes that are copied from or to memory. So again, Minos at runtime obtains the distribution, the distribution of the load of the requests of different sizes. And then it computes what is the overall load for small operations and for large operations. So since it knows already what is the threshold between small and large operations, it can compute this by just summing the load for small and large operations. So in this example, in red, we have the load for small operations, the sum of the load up to the threshold. And then we have in green the load for the large operations. It is instead the sum of the loads from the threshold on. Then the fraction of the load for small requests is, of course, the ratio between the red area and the sum of the red and the green area. Once this fraction of the load is obtained, the number of small cores is computed as the ceiling of the number of total cores times the fraction of the load for small operations. As for the last challenge, how we implement request dispatching, the main problem here, the main challenge we have to face is that the request size are unknown a priori, and also the clients do not know which one is a small core and a large core. So what could happen is that the RxQ of a small core receives a large request, the RxQ of a large core receives a small request, and ultimately these requests can be received in the wrong order by the cores. And to restore the order that we would like to have with size over sharding, we have that the large core has to send a small request to the small core, the small core has to send the large request to the large core, and this dispatching of the request is done in is done in software. And of course, this has an overhead, both in terms of latency and of throughput, and we want to reduce as much as possible this overhead. So to this end, what we do is that only small cores can read from the NIC, they can read from their own RxQs, and they can read from the RxQs of large cores. And then once a request is taken by a small core, the small core first obtains the size of the operation. For a put request, this is easy because the size of the item is in the header of the request. If it's a get, the core has to start processing the request by performing the lookup in memory. If the size of the request is small, then the small core simply proceeds and continues the request, processing the request. Otherwise, the request is dispatched to a large core. And in this way, we just incur the overhead, both in latency and in throughput, for the very few large operations that are indeed dispatched on the fly. So this concludes the implementation part of the technique. Let's see how it performs. We implement Minos on a server with 8 cores, a 40 gig NIC, and on top of a DPDK network stack. We use a workload that resembles the ETC Facebook workload, where less than 1% of the requests are large requests. By large request, we mean a request that hits an item whose size is between 1.5 and 500 kilobytes, and these are uniformly distributed in these between these two endpoints. Everything else is a small request that is also roughly uniformly distributed between 1 byte and 1.5 kilobytes. We use a read-dominated workload and a skewed workload, as is typical in this kind of settings. We compare Minos against 3 designs that are representative of 3 state-of-the-art systems. The first design is early binding, that is representative of Mica. The second one is early binding plus stealing, that is representative of what done by, for example, ZigOS. And the last one is late binding, that represents what is done by, for example, RAM Cloud. So let's see how these competitors work before delving into some numbers. In early binding, the mapping between the request and the core by which the request is processed is dependent on the key hash of the target item. So the client sends a request, and it encodes the key in the request, and depending on the key hash, this request is routed to a given RxQ, and subsequently to the corresponding core. In stealing, what happens is the same as in early binding, except that as soon as a core becomes idle, it can steal requests from other RxQs and from the buffer of other cores. And finally, in late binding, there is only one core that receives all the requests and dispatches them to worker cores as soon as these worker cores become idle. So the plot I'm going to show you is a throughput versus 99 percentile plot. On the x-axis, we have the throughput in millions of operations per second, and more to the right is better. On the y-axis, we have the 99 percentile latency in log scale in microseconds. So lower is better. The first comparison is between Minos and early binding. Minos is in red, early binding is in green. The first thing we see is that Minos achieves lower latency with respect to early binding, up to 1 order of magnitude better latency. And the reason is that Minos avoids headline blocking altogether. Instead, in early binding, it is sufficient that a small request and a large request collide on a given core by the key hash, and then headline blocking can happen. We also see that the two systems achieve the same throughput. Now, in early binding, we do not have any kind of software dispatch overhead. So this means that Minos is able to keep the dispatch overhead low, such that it doesn't hurt the throughput, the maximum throughput that it can achieve. Now let's see a comparison with stealing that is now here in black. We see that stealing substantially improves performance with respect to early binding by means of stealing. However, we still have that Minos achieves better latency, again, up to 1 order of magnitude better latency with respect to stealing. And the reason is that stealing helps in reducing the headline blocking problem only when the load is relatively low. As the load grows, the cores are rarely idle. And when they are rarely idle, it means that stealing kicks in rarely, and then the improvements given by stealing diminishes as the load increases. The last comparison is against late binding, that is in purple here. Again, we see that Minos achieves better latency, again, up to 1 order of magnitude better. But this time, the reason for this improvement is that Minos does not suffer from the combo effect. Minos always allocates some cores to small operations and then avoids the combo effect that instead can happen in late binding. Late binding is not affected by the headline blocking problem because requests are dispatched to cores only when they are idle. So there is no problem that a small request can be enqueued behind a large request. However, it can happen that the burst of large requests can take up the vast majority of the cores. We also see that Minos achieves higher throughput with respect to early binding, and this is because the throughput of early binding is bottlenecked by the throughput that the dispatching core can achieve. Actually, in this experiment, we had to use 2 dispatching cores to scale to this amount of throughput. So I said that there is a trade-off that Minos makes to improve the 99% latency, and I discussed this throughput with this slide. In this slide, I show the throughput of the system versus the 99th percentile only of large requests. So this means for this workload, we are looking at the 99.999th percentile of the latency. So it's the very, very tail. And we compare Minos against stealing, that is the second best approach in this case. And as we see, as the load grows, the penalty incurred by Minos grows. And before the system go into saturation at around 5.5 mega operations per second, the penalty of Minos is 2x. We have other results in the paper. We experiment with more identified distributions. We show that Minos can adapt to dynamic workloads by partitioning the cores at runtime depending on the workload that it witnesses. We also show that Minos can work with more write-intensive workloads and that it scales with additional network bandwidth available. So this is the last slide. I talked to you about size-aware sharding today. It is a technique to improve the tail latency in in-memory key-value stores. The main idea of size-aware sharding is to allocate and to serve small and large requests to different set of cores. And we have seen that the implementation of size-aware sharding in a Minos in-memory key-value stores can give up to 10 times lower latency, 99% latency with respect to existing approaches. And thank you for your attention. Be happy to take questions.
Hi, I'm Akshay from MIT. Can you describe why you use dynamic core reallocation instead of something like preemption to avoid head-of-line blocking?
The reason is mostly because of simplicity. We wanted, instead of disrupting this run-to-completion model that has been proposed in existing systems, we wanted something that could act before the serving of the request. So you can implement size-aware sharding in different architectures and different designs. For example, we have also an implementation of this on top of the late binding, as done for example, in RAM Cloud, where the dispatcher first checks what is the size of the operation and then dispatches it to the proper core depending on the size, and that works as well. So mostly it's because of that. There are other more technical details. Maybe we can talk about this later offline.
John Wilkes, Google.
Hello.
Curious, what happens if I also cared about the 95th percentile latency and the 99.9th percentile latency?
So if you care about the very tail, then this technique is going to give worse results, as I showed for the large request. The 95th percentile, in our case, it doesn't get worse. It still gets better than the competing approaches, because in this case, the heterogeneity is rather strong. But in any case, this approach works for a single metric of
Yes, which is exactly the thing that worries me a little.
Sorry?
Which is the thing that I was hoping you would notice. The fact that you're measuring and optimizing just one particular number.
It is absolutely works only for one. Yes, definitely.
Hi, Jiaqi from Harvard. So what is your core scheduling like? You're assigning different flows to different cores. Then how you're going to schedule the cores round robin?
So this uses basically the same approach used by Mica. So in particular, the concurrent read exclusive write version of Mica. So read requests are sent at random by the client to any of the cores, and write requests are sent to the core, to a specific core depending on the key hash. So they are roughly uniformly, the gets are roughly uniformly distributed, whereas the writes suffer from a little bit of skew.
Okay, so the next question is last section is about flow scheduling. How do you think their approach, such as hardware in the NIC, going to apply to your approach?
I'm sorry, can you repeat the
So
question?
if for different, for multiple queue approach or a hardware implemented things, are you going to say that this work is orthogonal, or you think that you cannot apply them to the hardware NIC?
I will have to think about how this thing would scale with different ways. I think that as long as you can redirect the request to another core, this can be applied. In the worst case, you can have that the software, you can have a single core that receives everything and then it dispatches everything to worker cores. This also works.
I see. Thank you.
Hi, Hafiz Mohsin from Tufts. So my question is, when you're grouping small and large cores, are you making any assumption about NUMA architecture?
Sorry, can you repeat it?
Non-uniform memory access.
Can you go closer to your mic?
So when you're grouping small and large cores, are you making any assumption about non-uniform memory access? NUMA architecture?
Can we take this offline? I'm not getting the question.
So okay, so when you are sort of having small cores and large cores, right?
Yes.
And you're sort of serving requests from the small cores, right? And are you making any assumption about the NUMA architecture where you have non-uniform memory access?
Sorry, I didn't get. You can implement this on a NUMA architecture where size-aware sharding happens within each NUMA domain. So mainly this is because of how requests are routed to the different RX queues. So basically what you would do is if you have two NUMA domains, you have two instances of the key value store, and each of these two instances runs Minos and the size-aware sharding.
Okay, let's thank the speaker again.